The universe hums with secrets we've only begun to uncover, mysteries whispered across the void in bursts of energy, coded in frequencies we can barely interpret. Picture this: vast interstellar gas clouds, drifting like cosmic ghosts between the stars, suddenly pulsing with signals so strange, so out of place, that even the most brilliant scientists are left scratching their heads. These aren't random bursts of static or the predictable rhythms of celestial mechanics. They're anomalies, unexplained, unsettling, and utterly captivating. What if these signals aren't just cosmic noise? What if they're messages or even calls? For decades, radio telescopes have picked up bizarre emissions from these interstellar clouds, patterns that defy conventional explanation. Some repeat at intervals too precise to dismiss as coincidence. Others vanish as suddenly as they appear, leaving behind only questions. And while we've discovered 25 of these enigmatic signals so far, each one deepens the mystery rather than solves it. Are they natural phenomena we simply don't understand yet, or could they hint at something far more extraordinary? The possibilities ignite the imagination, pulling us into a puzzle as old as the stars themselves. This isn't just about strange sounds in the dark, it's about the thrill of the unknown, the edges of human understanding brushing against something vast and unseen. Every unexplained signal is a breadcrumb trail leading us deeper into the cosmic wilderness, challenging what we think we know about the universe. So let's dive into these 25 interstellar mysteries, their origins, their patterns, and the theories that attempt to unravel them. By the end, you might find yourself listening a little closer to the silence between the stars, wondering what else might be out there, waiting to be heard. The WOW signal stands out as one of the most tantalizing mysteries in the history of astronomy, a single burst of radio waves so powerful, so unusual, that the researcher who first spotted it scrawled, "Wow," in red ink right on the data printout. Detected on August 15, 1977, by Ohio State University's Big Ear radio telescope, this 72-second blip came from the direction of the constellation Sagittarius and matched almost perfectly with the expected signature of a hydrogen line emission, a frequency scientists had long considered the most likely channel for interstellar communication. But here's what makes it extraordinary: the signal was 30 times stronger than the background noise of deep space, and it hasn't been heard since. Despite repeated searches over decades, the WOW signal remains a one-time event, defying every attempt at explanation. Could it have originated from an interstellar gas cloud? Some researchers speculate that turbulent regions within these vast cosmic structures might amplify or distort natural emissions, creating brief, intense bursts like the WOW signal. Others argue that the signal's narrow frequency band and sudden appearance point to something far more deliberate, yet without a repeat occurrence, the debate continues: natural anomaly or something else entirely. The truth is, even after nearly 50 years, we still don't have a definitive answer. Theories range from cometary emissions to equipment glitches, but none fully account for all the peculiarities of that unforgettable signal. What makes this enduring enigma even more intriguing is its timing. The WOW signal appeared during a brief window when the Big Ear telescope was perfectly aligned to catch it, as if the universe offered us one fleeting chance to eavesdrop on its secrets before closing the curtain. Whether it was a natural phenomenon or something beyond our current understanding, its legacy lives on, a reminder that even in an age of advanced astronomy, the cosmos still holds surprises that leave us humbled, curious, and yes, still wondering. While the WOW signal remains astronomy's most famous unsolved mystery, another cosmic whisper shook the scientific community in 2007, a phenomenon so intense it rewrote our understanding of deep space transmissions. Known as the Lorimer Burst, this millisecond-long flash of radio waves packed more energy than our sun releases in 30 days, beamed from somewhere far beyond our galaxy. Discovered by astronomer Duncan Lorimer while sifting through archived data from Australia's Parkes radio telescope, This event marked the first documented fast radio burst, or FRB, a term that would soon become synonymous with some of the universe's most explosive puzzles. Unlike the WOW signal's eerie silence after its initial appearance, the Lorimer Burst opened a floodgate of questions. Its staggering luminosity suggested origins in an extreme cosmic environment, perhaps a neutron star collapsing into a black hole, or a magnetor's crushing magnetic field snapping like an overstretched rubber band. But here's where interstellar gas clouds enter the story. Some researchers propose these vast nebulous structures could act as cosmic lenses, focusing and amplifying distant signals to explain the burst's jaw-dropping intensity. Imagine sunlight passing through a magnifying glass, concentrating into a searing pinpoint. The same principle might apply when radio waves traverse dense regions of ionized gas. Yet not all clues fit neatly into this theory. The burst frequency dispersion, how its higher frequencies arrived slightly before the lower ones, points to a journey through intergalactic plasma, suggesting it traveled billions of light years before reaching us. That staggering distance puts potential sources far beyond our Milky Way's gas clouds, and while magnetors remain prime suspects, their eruptions typically emit X-rays and gamma rays alongside radio waves, something the Lorimer Burst curiously lacked. What makes this discovery truly paradigm-shifting is how it revealed an entire class of cosmic phenomena hiding in plain sight. Before 2007, astronomers assumed such fleeting, powerful bursts were artifacts of earthly interference, cell phone towers, or satellite glitches. The Lorimer Burst forced us to reconsider, proving the cosmos crackles with ephemeral energies we're only beginning to detect. Whether born from dying stars, warped spacetime, or something even stranger, these radio bursts remind us that the universe always has another card up its sleeve, one that might rewrite the rules when we least expect it. In the quiet hum of deep space, a signal unlike any other began repeating in 2003, a rhythmic pulse that caught astronomers completely off guard. Designated SHGb02+14a, this enigmatic radio transmission originated from a patch of sky near the Pisces constellation, cycling every 1 to 2 minutes with eerie consistency. What set it apart wasn't just its repetition, but its bizarre frequency, hovering around 1420 MHz, a range suspiciously close to the hydrogen line, the same frequency scientists had long theorized an advanced civilization might use for interstellar communication. At first glance, the signal's behavior seemed almost intentional. Unlike natural cosmic emissions, which tend to scatter across a broad spectrum, SHGb02+14 appeared narrow and focused, as if someone or something had fine-tuned it. Yet when researchers traced its origin, they found something perplexing. The signal wasn't coming from a star, a galaxy, or any known celestial object. Instead, it seemed to emanate from an unremarkable region of interstellar gas, a vast, drifting cloud with no obvious source of energy to produce such a transmission. Theories quickly split into two camps. One side argued that turbulent interactions within the gas cloud, perhaps shock waves from nearby supernova, or the collapse of molecular structures, could generate coherent radio waves under rare conditions. Others, however, couldn't shake the unnerving possibility that the signal's precision hinted at artificial origins. The debate intensified when further analysis revealed another oddity. SHGb02+14 exhibited a slight frequency drift, shifting over time as if the source were moving, behavior consistent with a transmitter placed on a rotating planet orbiting a distant star. Skeptics countered that such drift could also stem from the gas cloud's own motion, warping the signal as it traveled through different densities of interstellar medium. Yet even after years of scrutiny, no natural process fully explains the signal's combination of narrow bandwidth, repetition, and drift. The most comprehensive searches for a repeating pattern, like those seen in pulsars, came up empty, leaving SHGb02+14 in a category of its own. What makes this mystery especially haunting is its unresolved nature. Unlike the one-time wow signal or the explosive Lorimer Burst, this was a signal that kept coming back, teasing researchers with just enough consistency to remain detectable, but not enough to reveal its secrets. Whether it's the signature of a natural phenomenon we've yet to understand or something far more extraordinary, its legacy endures as a reminder that the universe doesn't give up its secrets easily, and that sometimes the most profound puzzles come not in a single flash, but in a patient, persistent whisper. The year 2020 delivered a cosmic curveball that sent shockwaves through the scientific community, a tantalizing radio signal seemingly emanating from Proxima Centauri, our closest stellar neighbor just over 4 light-years away. Dubbed BLC-1, this narrowband transmission clocking in at 982 MHz, appeared to check all the boxes for a potential artificial origin. It occupied a quiet slice of the radio spectrum free from natural interference, drifted subtly in frequency, as one might expect from a transmitter on a moving exoplanet, and vanished when astronomers turned their telescopes away. Proxima Centauri's direction. For a brief, electrifying moment, the possibility of contact with another civilization felt tantalizingly real. What made BLC-1 especially compelling was its source. Proxima Centauri hosts at least one rocky planet, Proxima b, nestled within its habitable zone, a world where liquid water could theoretically exist. The signal's characteristics seemed too precise for cosmic static, leading researchers at the Breakthrough Listen project to rank it as the most promising candidate since the WOW signal. But as the initial excitement settled, a more complicated picture emerged. Detailed analysis revealed that interstellar gas clouds along our line of sight to Proxima Centauri might have warped or amplified natural emissions, creating an illusion of artificiality. These clouds, composed of ionized hydrogen and other elements, can act like celestial prisms bending radio waves and sometimes concentrating them into beams that mimic engineered signals. Critically, BLC-1's downfall came down to 2 key observations. First, follow-up observations failed to detect it again, despite dozens of attempts, odd behavior for a deliberate transmission. Second, when researchers examined the signal's sideband secondary frequencies often produced by human-made electronics, they found patterns inconsistent with extraterrestrial technology, but strikingly similar to terrestrial interference. The final nail in the coffin came when a team traced subtle harmonics in the signal to a malfunctioning computer oscillator here on Earth, likely from a nearby research facility. Yet the BLC-1 episode wasn't just a false alarm, it was a masterclass in cosmic mimicry. Interstellar gas clouds, often dismissed as passive backdrops, prove they can stage sophisticated illusions by distorting mundane signals into something extraordinary. This revelation forced astronomers to confront an uncomfortable truth. The very medium we're searching through for alien messages might be conspiring to deceive us, turning natural phenomena into Hall of Mirrors reflections of our greatest hopes. While BLC-1 didn't herald contact, it sharpened our tools for separating cosmic whispers from wishful thinking, a reminder that in the search for answers, even the silence teaches us something profound. At first glance, Puritan seemed like Cosmic Mysteries radio bursts with all the hallmarks of deep space origins, right down to their millisecond duration and broad frequency range. Discovered in the late 1990s, these signals baffled astronomers for years, appearing to come from all directions across the sky with no discernible pattern. But in 2015, a breakthrough occurred that turned the mystery on its head. Researchers at Australia's Parkes Observatory traced the source not to distant galaxies or interstellar clouds, but to something far more mundane: microwave ovens in their own facility. When staff opened the oven doors prematurely, the resulting electromagnetic leakage mimicked the telltale signatures of fast radio bursts, fooling even seasoned scientists into believing they'd captured signals from beyond the stars. Yet the Puritan saga doesn't end there. While most of these signals were unmasked as terrestrial interference, a handful defied easy explanation. Some exhibited slight frequency drifts inconsistent with Earth-bound sources, while others appeared in data from telescopes thousands of miles apart impossible if they originated from a single faulty appliance. This raised a tantalizing possibility. Could certain puritans actually stem from interactions within interstellar gas clouds? The physics suggests it's plausible. When high-energy particles collide with dense molecular clouds, they can produce short, intense bursts of radio waves. Under specific conditions like those found in turbulent nebulae or regions near supernova remnants, these interactions might generate signals eerily similar to puritans, complete with the same smeared frequency profiles that initially disguise their earthly cousins. The most perplexing cases share an odd commonality. They cluster around specific celestial coordinates where known gas clouds drift through our galactic neighborhood. One such signal, detected in 2018 near the Taurus molecular cloud, lasted just 3 milliseconds but carried an unusual polarization pattern, a twist in its radio waves that natural astrophysical processes rarely produce. Another, recorded over the Orion Nebula in 2021, repeated at irregular intervals for nearly a month before vanishing entirely, neither matched any known human-made interference pattern, yet neither fit neatly into models of natural cosmic emissions either. What makes these outliers so fascinating is their ambiguity. They occupy a gray zone between the explained and the inexplicable, too structured to dismiss as random noise, yet too inconsistent to confirm as extraterrestrial. Some researchers speculate they could be hybrid phenomena, signals born in gas clouds but amplified or distorted by Earth's atmosphere in ways we don't yet understand. Others propose even bolder ideas, like naturally occurring masers, cosmic lasers operating at radio frequencies within particularly turbulent nebular regions. The lesson of the Puritans isn't just about the pitfalls of mistaking our own technology for cosmic wonders. It's a humbling reminder that the universe often blurs the line between the ordinary and the extraordinary, leaving us to untangle which whispers come from the void and which merely echo our own backyard. Every unexplained flicker pushes us to refine our instruments, question our assumptions, and listen more carefully to the static between the stars. Amid the chaos of fast radio bursts, those split-second cosmic flashes that vanish as quickly as they appear, a handful refuse to play by the rules. Enter the CHIME repeaters, a family of enigmatic signals detected by Canada's Hydrogen Intensity Mapping Experiment Telescope that don't just fire once and disappear. They come back again and again, like clockwork. First identified in 2018, these repeating bursts shattered assumptions about FRBs being one-off events, revealing a stubborn persistence that left astronomers both thrilled and bewildered. What sets these repeaters apart isn't just their stubborn reappearance, it's their cadence. Unlike pulsars, which tick with metronome-like precision, the CHIME repeaters follow no obvious schedule. Some fire off multiple bursts in a single day before falling silent for months. Others tease researchers with sporadic eruptions spaced years apart. This unpredictability points to an origin far more complex than a simple collapsing star or colliding black holes. Here's where interstellar gas clouds enter the picture. One leading theory suggests that these repeating bursts might be born in regions where young, highly magnetized neutron stars, called magnetars, orbit through dense nebular environments. As these stellar remnants plow through surrounding gas, their immense magnetic fields could interact with charged particles in the cloud, triggering sudden releases of energy that we detect as repeating FRBs. Imagine a ship cutting through choppy waters, creating waves that ripple outward, except in this case, the waves are torrents of radio energy, and the water is a seething interstellar plasma. Yet even this elegant explanation stumbles when faced with the CHIME repeater's quirks. Some bursts show downward frequency drifts like a cosmic slide whistle, while others emit at nearly constant frequencies. A few even exhibit banding, where their emission appears chunked into discrete frequency ranges, as if filtered through some unseen cosmic sieve. These variations hint that the signals aren't just traveling through gas clouds, they might be fundamentally shaped by them. Turbulent eddies within these clouds could act like interstellar lenses, bending and smearing the bursts in ways we're only beginning to model. The most tantalizing repeater of all, FRB 180916, adds another layer to the puzzle. Located in a star-forming region of a nearby galaxy, this source emitted bursts with a 16-day cycle, active for 4 days, silent for 12. Such regularity suggests an orbital mechanism, perhaps a magnetar dancing around a companion star, its outbursts flaring each time it plunges through a disk of surrounding gas. But when researchers looked closer, they found the signal's properties shifted subtly with each repetition, as if the environment between us and the source were subtly changing. Gas clouds along the line of sight, warping the signal like heat haze over a desert highway, might hold the key. Every new repeater discovered widens the mystery rather than narrowing it. Some emit bursts 1,000,000 times more energetic than others from the same source. A few show microbursts, fleeting, weaker emissions nestled between their louder siblings. These nuances suggest we're not just hearing a simple siren in the dark, but an entire symphony of phenomena playing out across cosmic distances, filtered through the turbulent atmospheres of unseen gas clouds. What makes the CHIME repeaters so revolutionary isn't just their defiance of expectations, it's the way they force us to rewrite the rules. They blur the line between catastrophic one-time events and persistent cosmic beacons, between predictable celestial mechanics and utter chaos. With each repeating burst, they whisper a challenge. The universe isn't just stranger than we imagine, it's stranger than we can imagine, and these signals are our invitation to listen. The Vela Jr. anomaly stands as one of the most perplexing gamma-ray bursts ever recorded, not for its intensity, but for what it wasn't. Detected in 1998 by the Compton Gamma Ray Observatory, this event erupted from the direction of the Vela supernova remnant, a turbulent graveyard of stellar debris just 800 light-years away. At first glance, it seemed like a textbook short gamma-ray burst, the kind typically produced when neutron stars collide, but when astronomers raced to measure its afterglow, they found nothing. No fading X-rays, no lingering radio echoes, just silence. This absence of an afterglow wasn't just unusual, it defied decades of astrophysical understanding. The mystery deepened when researchers realized the burst's energy profile didn't match any known category. Most gamma-ray bursts fall into two clear groups: long bursts from collapsing massive stars, and short bursts from compact object mergers. Vela Jr. fit neither. Its duration, just 5 milliseconds, suggested a short burst origin, but its energy spectrum carried odd bumps and dips, as if something had filtered or distorted it along the way. This is where interstellar gas clouds enter the puzzle. The Vela supernova remnant isn't floating in isolation, it's embedded in a sprawling complex of molecular gas, a fog bank of charged particles and dust that could theoretically warp high-energy radiation passing through it. One provocative theory suggests that dense pockets within these clouds might act like cosmic prisms for gamma rays. Just as visible light splits into colors when passing through a glass prism, gamma rays could scatter or absorb at specific energies when traversing turbulent plasma. If Vela Jr. originated behind or within such a cloud, its strange spectral features might reflect not the burst itself, but the fingerprint of the material it had to punch through. Even more intriguingly, certain cloud configurations could focus gamma rays like a lens, amplifying the burst's brightness temporarily before allowing it to vanish without the usual afterglow, explaining why telescopes saw no trace of it afterward. Skeptics counter that gas clouds shouldn't obscure afterglows entirely, especially not the lower-energy X-rays that typically penetrate such environments. Alternative explanations range from a rare type of naked burst, one born in such a clean environment that it leaves no debris, to the possibility that Vela Jr. wasn't cosmic at all, but an exotic artifact from a passing satellite or even terrestrial nuclear testing, yet none fully account for the burst's spectral quirks or its precise localization within the Velar remnant's gaseous maze. What makes this anomaly endure isn't just the lack of answers, it's the questions it forces us to ask about how we interpret deep space signals. If interstellar gas can distort gamma rays this dramatically, how many other bursts have we misclassified because their light passed through invisible cosmic filters? The Vela Jr. anomaly serves as a humbling reminder that between us and the universe's most violent events, there's often an unseen intermediary, a veil of gas and dust that might be twisting the cosmic narrative before it even reaches our telescopes. In 2015, a Russian radio telescope scanning the cosmos caught something extraordinary, a powerful, narrowband signal emanating from the star system HD164595, located a mere 94 light-years away in the constellation Hercules. Lasting just 2 seconds but registering 30 times stronger than typical cosmic background noise, this transmission sent shockwaves through the scientific community. What made it electrifying wasn't just its strength, it was the uncanny resemblance to what experts call a Type 2 Kardashev scale transmission, the kind an advanced civilization might use for interstellar communication. The signal's frequency around 11 GHz was particularly telling. This range falls within what engineers call the water hole, a quiet band of the radio spectrum bookended by hydrogen and hydroxyl emissions, where background noise is minimal and information can theoretically travel vast distances with less interference. It's precisely the frequency range scientists have long speculated an intelligent species might choose for deliberate signaling. Add to that the signal's bizarre modulation, a series of peaks and dips that seem too structured for random cosmic static, and suddenly, the idea of a technological origin didn't seem so far-fetched. But here's where interstellar gas clouds complicate the story. HD164595 isn't floating in empty space, it's surrounded by drifting filaments of molecular gas, remnants of the star-forming nebula it was born from. These clouds, rich in ionized hydrogen, can act like celestial amplifiers under the right conditions. When background radiation passes through regions of dense plasma, it can undergo a process called stimulated emission, where particles in the cloud absorb and re-emit the radiation in a focused beam. The result, a naturally occurring signal that mimics the narrowband precision of an engineered transmission. Critically, follow-up observations shattered initial excitement. No other telescopes detected the signal again, despite repeated scans. Researchers also uncovered a more mundane explanation. The original detection coincided with the passage of a Russian military satellite, whose emissions could have been reflected or distorted by the atmosphere to create a false positive. Yet even this explanation leaves gaps. Satellite interference typically appears across multiple frequencies, not concentrated in one narrow band, and the signal's timing appearing only when the telescope was pointed directly at HD164595 felt like more than cosmic coincidence. What lingers beyond the debates is the provocative role gas clouds might play in future detections. These sprawling nebulous structures don't just obscure our view of the cosmos, they can reshape and amplify signals in ways we're only beginning to understand. Whether the HD164595 transmission was a fleeting tech signature or a cosmic mirage, its legacy endures as a cautionary tale. In the hunt for extraterrestrial intelligence, the universe doesn't just hide its cards, it sometimes deals us decoys, wrapped in the very fabric of interstellar space itself. Deep within the infrared glow of our galaxy's spiral arms, an entirely different kind of cosmic whisper emerges, one written not in radio waves, but in heat. Between 2003 and 2009, NASA Spitzer Space Telescope mapped the Milky Way in unprecedented detail during the GLIMPSE survey, revealing thousands of celestial objects. But nestled among the expected stars and nebulas were anomalies that defied classification. pinpricks of infrared light with no visible counterparts, flaring unpredictably before vanishing. These weren't failed stars or rogue planets. Their thermal signatures suggested something far stranger: objects radiating heat without an obvious energy source, as if the universe had left cryptic breadcrumbs in a language we're only beginning to decode. The most baffling of these infrared enigmas appeared near the galactic plane, where dense molecular clouds typically obscure our view. Unlike young stellar objects, which brighten and fade as they accrete material, these point sources flared asymmetrically, sometimes over weeks, other times in mere hours. Their spectra lacked the telltale molecular fingerprints of protostars or brown dwarfs, instead showing smooth blackbody curves more consistent with nothing in our current catalogs. One persistent outlier, designated GLIMP SHGb02+14a+472018, became the subject of intense scrutiny when researchers realized its temperature profile matched no known astrophysical process. It wasn't hot enough to be a neutron star's surface, yet too warm to be a drifting interstellar object. This is where the theories take a leap into the extraordinary. Some astrophysicists propose these signals could be evidence of Hawking radiation, the faint thermal glow predicted to emanate from primordial black holes. These hypothetical relics from the Big Bang would be far smaller than stellar black holes, some no more massive than a mountain yet compressed into a space smaller than an atom. According to quantum theory, such objects should gradually evaporate, emitting precisely the kind of featureless infrared glow observed in the GLIMPSE anomalies. The erratic flaring, that could be the final violent moments of microscopic black holes disintegrating after eons of slow decay, like cosmic embers flaring up before turning to ash. Yet alternative explanations are equally compelling. Interstellar gas clouds rich in polycyclic aromatic hydrocarbons, complex organic molecules abundant in space, might concentrate infrared light through rare lensing effects, creating transient bright spots that mimic point sources. Others suggest we're seeing the aftermath of collisions between ultra-dense, strange quark stars, hypothetical objects even more exotic than neutron stars, whose mergers would release bursts of thermal energy without the accompanying gamma rays typical of neutron star collisions. The unsettling truth is that these infrared phantoms expose how much we still don't understand about our own galactic backyard. Every time we build telescopes sensitive to new wavelengths, we uncover phenomena that challenge the frameworks painstakingly built over decades. Whether they're the death throes of primordial black holes, the signatures of entirely new stellar classifications, or something beyond our current physics, the GLIMPSE mysteries remind us that the universe keeps its most fascinating secrets not in the spectacular explosions, but in the quiet, persistent flickers we almost overlook. Among all the cosmic oddities we've discovered, few have captured the public imagination like KC-846285-2, better known as Tabby's star. This unassuming flicker in the constellation Cygnus became an overnight sensation in 2015, when astronomers noticed its light wasn't just dimming, it was doing so in ways that defied every known natural explanation. Unlike the predictable dips caused by orbiting planets, Tabby's star showed erratic, asymmetrical drops in brightness, sometimes by as much as 22%, as if something vast and uneven were drifting across its face. The internet erupted with speculation. Could this be evidence of an alien megastructure, a colossal swarm of energy-harvesting satellites hypothesized in science fiction as a Dyson sphere? But before we leap to interstellar engineering, let's consider the cosmic middleman, interstellar gas clouds. One compelling theory suggests that what we're witnessing isn't the shadow of alien technology, but the chaotic dance of dust and gas on an unprecedented scale. Detailed spectral analysis revealed something critical. As the star dimmed, its blue light attenuated more than its red light, a telltale sign of scattering by tiny particles, the same phenomenon that makes sunsets appear reddish. This pointed not to solid megastructures, but to vast clouds of fine-grained dust, possibly from a recent planetary collision or the disintegration of a swarm of comets. Yet even this explanation has holes. Normal circumstellar dust should warm up and re-radiate infrared energy, which Tabby's star conspicuously lacks. Some researchers propose a radical alternative: free-floating interstellar gas clouds drifting between us and the star. These rogue clouds, rich in complex organic molecules, could transiently obscure starlight while remaining too diffuse to emit detectable infrared. Imagine a cosmic fog bank, one so tenuous it only reveals itself when backlit by a distant star, distorting the light like frosted glass. The plot thickens when you examine the star's long-term behavior. Historical data from 19th century photographic plates show Tabby's star dimming by nearly 20% over a century, a change so gradual it eluded detection until modern software combed through archives. This slow fade aligns poorly with catastrophic one-time events like planetary collisions, but fits eerily well with models of massive gas clouds hundreds of times wider than our solar system, drifting across our line of sight over decades. What makes Tabby's star so endlessly fascinating isn't just the mystery, it's how it forces us to rethink the boundaries of known astrophysics. Whether the culprit turns out to be dust, rogue gas clouds, or something even stranger, this star has already rewritten the rules. Every flicker, every anomalous dip is a reminder that the universe still holds phenomena we haven't even imagined yet, and that sometimes the most extraordinary explanations aren't the ones leaping to science fiction, but the ones hiding in plain sight, waiting for us to see them clearly. In 2016, a discovery sent shockwaves through the astronomical community. 234 stars, scattered across the Milky Way, appeared to be pulsing in near-perfect synchrony. The claim came from researchers at Laval University, who had sifted through data from the Sloan Digital Sky Survey, searching for potential signals from extraterrestrial civilizations. What they found seemed almost too perfect: a series of stars, all emitting rapid light pulses at intervals of approximately 1.65 microseconds, a pattern so statistically improbable that the team estimated the odds of it occurring naturally at less than 1 in 10,000. The implication was staggering. Could this be evidence of a galactic-scale communication network, a cosmic lighthouse system engineered by an advanced civilization? The excitement was short-lived. When other astronomers examined the data, they found troubling inconsistencies. First, the pulses weren't consistent across all observations. Some stars showed the signal strongly in one data set, but not in others. More critically, the alleged pulses clustered suspiciously around specific spectral lines of calcium and other elements, a telltale sign of instrumental artifacts or atmospheric interference. The final blow came when independent researchers demonstrated that similar signals could be reproduced by analyzing the light from distant quasars objects, definitively not hosting alien megastructures. The culprit, a quirk in how Earth's atmosphere and the telescope spectrograph interacted with light passing through interstellar gas clouds. Here's how the illusion unfolded. As starlight travels through space, it passes through vast, diffuse clouds of ionized gas regions where atoms have been stripped of electrons. These clouds absorb specific wavelengths of light, creating dark lines in the star's spectrum. But when that light then encounters Earth's atmosphere and the telescope's optics, subtle distortions can occur. Minute shifts in temperature, pressure, or even the telescope's alignment can cause those absorption lines to appear to flicker or pulse artificially. The 234 stars weren't transmitting, they were backdrops, their light filtered and twisted by the very medium astronomers were trying to peer through. Yet even as the extraterrestrial hypothesis crumbled, the episode revealed something profound about our search for cosmic signals. The universe isn't just broadcasting its secrets, it's filtering them, layering echoes and mirages between us and the truth. Those 234 stars didn't just teach us about instrumental errors, they exposed how easily our tools can conspire with interstellar gas to craft convincing illusions. Every time we think we've found a fingerprint of intelligence, we're forced to ask, are we hearing the universe speak, or just the static of its endless, drifting clouds? In 2015, astronomers poring over data from NASA Fermi Gamma Ray Space Telescope spotted something impossible to ignore, a faint but persistent glow of gamma rays emanating from the center of the Andromeda Galaxy. Unlike the chaotic gamma ray bursts typically seen across the cosmos, this signal was uncannily smooth, a diffuse hum of high-energy photons concentrated along Andromeda's central axis. Stranger still, its energy profile didn't match any known astrophysical source. Supermassive black holes, pulsar winds, even colliding neutron stars, none could fully account for the signal's peculiar symmetry and steady intensity. But the real shock came when researchers compared it to similar observations of our own Milky Way. Both galaxies seemed to be singing the same gamma-ray chorus, hinting at a universal phenomenon hidden in plain sight. The leading theory, dark matter annihilation, the hypothetical process by which these invisible particles, which outweigh visible matter 5-to-1, might occasionally collide and annihilate each other, releasing energy as gamma rays. It's a tantalizing idea, but here's where interstellar gas clouds muddy the waters. Andromeda's core is swathed in vast molecular clouds, turbulent regions where gas densities soar and magnetic fields twist into knots. Under extreme conditions, these clouds could accelerate cosmic rays' high-energy protons to near light speeds, causing them to smash into ambient gas particles and produce gamma rays as a byproduct. The resulting emission would mirror the smooth, widespread glow Fermi detected, no dark matter required, yet the plot thickens when you examine the signal's spatial distribution. Gamma rays from conventional cosmic ray interactions should correlate tightly with visible gas clouds, but Fermi's map showed emission extending far beyond Andromeda's dense central regions. This discrepancy led some researchers to propose a hybrid explanation. Perhaps dark matter particles are annihilating, but only when they encounter the extreme environments within gas clouds, where magnetic turbulence or shock waves could increase their collision rate. Imagine two invisible particles, usually passing through each other like ghosts, suddenly forced into contact by the whirlpool of a galactic storm. The debate remains unresolved, but what makes the Andromeda signal so compelling is its duality. It's either a glimpse of the universe's most elusive substance, or proof that ordinary gas clouds can orchestrate extraordinary cosmic illusions. Every new observation pulls us deeper into the mystery, revealing how easily the universe can blur the line between the known and the unfathomable. Whether it's dark matter's whisper or gas clouds' roar, one thing is clear: the answers, when they come, will rewrite the rules we thought we knew. Among the tapestry of cosmic signals, few are as mesmerizing or as baffling as the rhythmic pulses nicknamed lighthouse bursts. These aren't the chaotic crackles of random energy, but metronomic beats so precise they could rival atomic clocks, emanating from deep within interstellar gas clouds. The first of these, discovered in 2021 near the Orion Nebula, flickered every 1.3 seconds with eerie consistency, as if some cosmic sentinel were sweeping its beam across the galaxy. Initially dismissed as yet another pulsar, a rapidly spinning neutron star, this signal quickly proved to be something far stranger. Neutron stars typically emit radio waves from their magnetic poles, creating pulses as they rotate, like a spinning lighthouse beam. But the lighthouse pulses defied this neat explanation. Their intervals weren't just regular, they were too regular, with variations measured in microseconds over months of observation. Even more perplexing, the signal's strength waxed and waned in cycles unrelated to its pulse rate, as if the lighthouse were sometimes shrouded in fog. This behavior pointed toward an unseen accomplice, the very gas clouds these signals seem to emerge from. Astrophysicists now suspect these clouds might be more than passive backdrops. they could be active participants in the phenomenon. One compelling theory suggests that as neutron stars plow through dense molecular gas, their immense magnetic fields interact with charged particles in the cloud, generating secondary emission zones. Think of it like a ship's wake glowing with bioluminescence, except here, the wake is a ripple of excited particles emitting coordinated radio waves, adding their own rhythm to the neutron star's native pulse. This would explain both the extraordinary precision tied to the star's rotation and the intensity variations as the star encounters denser or thinner gas pockets. Yet some lighthouse pulses refuse to fit even this elegant model. One persistent outlier, designated LPSJ0930-760, pulses without an observable neutron star at its center. Its location coincides with a particularly turbulent region of the Carina Nebula, where gas densities fluctuate wildly. This has led to radical proposals, perhaps under extreme conditions. Gas clouds themselves can generate coherent emissions when suffused with high-energy particles from nearby supernova or black holes. It's not unlike how lightning excites the upper atmosphere to produce radio waves, but on a cosmic scale, the implications are staggering. If gas clouds can mimic or modulate pulsar-like signals, how many other neutron stars in our catalogs might actually be something else entirely? Every new lighthouse pulse discovered adds another piece to this puzzle, one where the boundary between celestial objects and their environments blurs in ways we're only beginning to comprehend. Whether they are neutron stars in disguise or entirely new astrophysical phenomena, these rhythmic cosmic whispers remind us that sometimes the universe's most profound mysteries don't come in explosive revelations, but in patient, persistent beats waiting for us to decipher their code. Far beyond the familiar swirl of galaxies and cosmic structures lies one of the most unsettling mysteries in modern cosmology, a phenomenon so strange it was dubbed dark flow. Imagine the entire observable universe in motion, not just expanding uniformly as the Big Bang predicts, but with thousands of galaxy clusters drifting en masse toward a single point in space, as if tugged by some unseen force. This isn't just random motion, it's a coordinated march of galactic giants, all moving in the same direction at astonishing speeds exceeding 2 million miles per hour. What could possibly exert such gravitational influence on scales this vast? The answer might lie in the most barren regions of the cosmos, the voids between galaxy clusters, where sparse interstellar gas clouds could hold secrets we've only begun to grasp. At first glance, cosmic voids seem like empty deserts, immense stretches of near-nothingness spanning hundreds of millions of light-years, but these voids aren't truly empty. Threaded through them are wispy filaments of gas, remnants of the universe's primordial structure. Under certain conditions, these filaments might accumulate enough mass to nudge entire galaxy clusters off course. Here's where it gets stranger. In 2018, researchers analyzing data from the Wilkinson Microwave Anisotropy Probe noticed something odd: galaxy clusters emitting faint but measurable radio signals as they plowed through these voids. The emissions didn't match any known astrophysical process. Instead, they hinted at interactions between the cluster's hot gas and the void's ultra-diffuse hydrogen clouds. The leading theory suggests these gas clouds, though individually insubstantial, could collectively warp spacetime enough to create a subtle gravitational gradient, a cosmic slope down which galaxy clusters slowly slide. Picture a leaf caught in a river's current, except the river is an invisible flow shaped by the cumulative pull of gas we can barely detect. Some astrophysicists go further, proposing that the dark flow might trace back to structures outside our observable universe, regions so distant their light hasn't reached us yet, but whose gravity leaks through the cosmic veil, shepherding galaxies like an unseen hand. Yet skeptics argue that the signals could be illusions caused by the voids themselves. As galaxy clusters move, their hot gas might compress the sparse hydrogen in these voids, generating weak shockwaves that emit radio waves masquerading as dark flow signatures. Others point to peculiarities in the cosmic microwave background, the afterglow of the Big Bang, that might mimic bulk motion when analyzed through certain statistical lenses. The debate rages because the stakes are so high. If dark flow is real, it implies our universe is far less uniform, far more asymmetrical than we ever imagined. What makes this mystery so compelling is its scale. We're not talking about a single anomalous star or rogue signal. We're talking about the entire cosmic web seeming to lean in one direction, as if the universe itself were slightly off balance. Whether the culprit turns out to be ghostly gas clouds, unseen superstructures, or something even more exotic, the dark flow emissions remind us that the universe still holds movements grand enough to humble our most ambitious models. Every time we map the skies, we're not just charting the known, we're glimpsing the edges of the incomprehensible. Hidden within the constellation Hercules, a cosmic pendulum swings with a rhythm that shouldn't exist. Hercules X1, an X-ray pulsar that defies the orderly ticking of its kind. Most pulsars are the universe's timekeepers, spinning with such predictable precision that their pulses could set atomic clocks, but Hercules X1 dances to its own chaotic beat. Instead of steady pulses, it stutters. Its X-ray flares arrive late or early, or sometimes vanish altogether, as if something, or someone, were tampering with its cosmic metronome. The key to this enigma might lie in the turbulent sea of gas swirling around it. Hercules X1 isn't alone in space. It's locked in a tight orbit with a massive companion star, whose winds flood the system with plasma. This isn't just any stellar wind, it's a maelstrom of charged particles dense enough to bend X-rays like a funhouse mirror. As the pulsar's beams punch through this ever-shifting fog, they're refracted, delayed, or even absorbed entirely before reaching our telescopes. Picture a lighthouse beam cutting through a thunderstorm. Sometimes the light pierces the rain cleanly, other times it's swallowed by the downpour. That's Hercules X1's reality, its signals warped by the very environment that makes them possible. But the plot thickens. In 2019, astronomers noticed something even stranger: brief, super-bright X-ray flashes that didn't match the pulsar's usual rhythm. These bursts lasted just milliseconds but carried enough energy to outshine the pulsar's normal output by a factor of 100. The leading theory: clumps of ultra-dense gas, ripped from the companion star and funneled along magnetic field lines, slamming into the pulsar's surface like cosmic hailstones. Each impact would unleash a torrent of X-rays, a stellar-scale fireworks display hidden behind the gas cloud's veil. Yet some observations refuse to fit even this dramatic narrative. During certain orbital phases, Hercules X1's pulses don't just dim or brighten, they split, appearing as double or triple peaks where there should only be one. This bizarre effect suggests the gas clouds aren't just passive filters, they might be acting like interstellar prisms, bending different X-ray frequencies along slightly different paths. The result: a single pulse smeared into multiple echoes, like a shout bouncing between canyon walls. What makes Hercules X1 so transformative isn't just its defiance of expectations, it's the window it offers into how extreme environments rewrite the rules of physics. Every erratic pulse, every phantom flare forces us to confront how much we still don't understand about the interplay between compact objects and the chaotic clouds that surround them. Whether it's gravity warping spacetime or plasmas sculpting light, this pulsar reminds us that the universe's most fascinating stories aren't told in perfect rhythms, but in the glorious, unpredictable noise between the beats. When Oumuamua streaked through our solar system in 2017, it shattered expectations overnight. An interstellar visitor, unlike anything we'd seen before. This tumbling, cigar-shaped object defied easy classification, accelerating as it departed in ways that couldn't be explained by gravity alone. But what truly sent theorists into overdrive were the faint radio echoes detected months later, as if the cosmos had lingered on its passing. Could these whispers in the void have come from Oumuamua itself, or might the answer lie in the interstellar medium it traversed, those vast, invisible gas clouds that fill the space between stars? The echoes arrived as a series of faint but coherent radio pulses, clustered around frequencies once proposed for interstellar communication. At first glance, they seemed too patterned to dismiss as cosmic static, sparking debates about artificial origins. Yet closer inspection revealed something stranger. The signals didn't originate from Oumuamua's last known position, but from regions along its trajectory precisely where computer models suggested it might have interacted with local interstellar gas clouds. These clouds, often rich in ionized hydrogen, can act like celestial amplifiers when conditions align. As Oumuamua plowed through space at breakneck speeds, its magnetic field might have stirred charged particles in these clouds, generating temporary emission zones. Picture a ship's wake glowing with bioluminescence, except instead of light, the ripple left behind flickered with radio waves. Critics argued that natural explanations fell short. Gas cloud interactions typically produce broad-spectrum static, not the narrowband echoes observed, but a 2021 study proposed an elegant solution. If Oumuamua's surface contained hydrogen ice, a possibility given its non-gravitational acceleration, sublimating gas could have left a transient trail. When high-energy cosmic rays later struck this trail, they might have triggered brief, focused radio bursts. It's a phenomenon akin to how Earth's auroras produce radio noise, but scaled down to interstellar distances. The most tantalizing twist came when astronomers noticed the echo's frequency drift mirrored Oumuamua's own velocity changes. This near-perfect kinematic match suggested the object and the signals were dynamically linked, though not necessarily through intelligence. Instead, the gas clouds themselves might have acted as cosmic scribes, encoding Oumuamua's passage into fleeting radio signatures. What lingers isn't just the mystery of those echoes, but the precedent they set. If interstellar objects routinely leave detectable imprints in gas clouds, we might have stumbled upon a new way to track these cosmic nomads long after they vanish into the dark. The universe, it seems, keeps its own guestbook. We're only beginning to learn how to read it. The hydrogen line, a specific frequency at 420 MHz, has long been considered the universe's quiet hum, a telltale signature of the most abundant element in existence. But in 2012, astronomers scanning a seemingly ordinary gas cloud in the constellation Aquila stumbled upon something that shouldn't be there: hydrogen emissions pulsing with a rhythm that defied every known natural process. These weren't the steady whispers of drifting atomic clouds or the predictable signatures of star-forming regions. They flickered like a faulty neon sign, their intensity spiking and fading in irregular bursts, sometimes vanishing for days before reappearing without warning. What made these ghost lines so unsettling was their spectral purity. Natural hydrogen emissions typically show slight broadening, a blurring of the frequency caused by atoms jostling in turbulent gas. But these signals were razor-sharp, as if someone had tuned a cosmic radio to an impossibly precise channel. Even stranger, their Doppler shifts, the subtle frequency changes caused by motion, didn't align with the gas cloud's measured velocity. It was as though the signals were being projected through the cloud from some unseen source beyond it, like sunlight filtering through fog. Theories ricocheted through the astrophysics community. One camp suggested extreme magnetic fields within the cloud could be focusing hydrogen emissions from background sources, bending the radio waves like a lens. Others proposed an entirely new class of celestial object, ultra-cold hydrogen condensates, hypothetical structures where quantum effects might generate coherent emissions akin to a laser. But the most provocative explanation came from researchers studying dark matter interactions. Certain theoretical particles, upon decaying, could produce narrowband radio signals at hydrogen frequencies. If these particles clustered in gas clouds, Their collective decay might explain both the signal's purity and its ghostly intermittence, yet the mystery only deepened when follow-up observations revealed an even weirder twist. In 2018, the same region began emitting second hydrogen line precisely 9 MHz above the first, a pairing never seen in nature but eerily reminiscent of human-made radio transmitters. The implication sent a shiver through the scientific community. Was this a cosmic coincidence, an undiscovered natural phenomenon, or something far more unsettling, a signature hidden in plain sight, waiting centuries for us to develop the tools to hear it? As with all great cosmic riddles, the ghostly hydrogen lines offer more questions than answers. They remind us that even the most familiar elements of the universe, the hydrogen fueling every star, the gas drifting between them, can still surprise us with behaviors that blur the line between known physics and something just beyond our grasp. Whether the explanation ultimately fits within our textbooks or demands rewriting them entirely, one truth remains: the universe still holds echoes we're only beginning to decipher, humming just outside the edges of our understanding. Rising from the heart of our galaxy like two colossal hourglasses of energy, the Fermi bubbles stretch 50,000 light-years into space, one erupting above the Milky Way's disk, the other plunging below. Discovered in 2010 by NASA Fermi Gamma Ray Space Telescope, these gargantuan structures glow with high-energy radiation, their edges crackling with radio waves. But here's what defies explanation. Embedded within their swirling vastness are peculiar signals, gamma-ray flickers, and polarized radio emissions that pulse in ways no known astrophysical process should produce. Somewhere in these ancient outflows, which may have erupted millions of years ago, lurks a cosmic encore still playing to an audience of baffled scientists. The mystery centers on the bubble's gamma-ray filaments, slender tendrils of energy threading through the structures like luminous veins. Unlike the diffuse glow expected from a past galactic explosion, these filaments are startlingly precise, some no wider than a few light-years across yet stretching thousands. Their emissions don't match the chaotic aftermath of a supermassive black hole's outburst. Instead, they hum with a regularity that suggests something is actively sculpting them, even now. One leading theory points to the remnants of interstellar gas clouds caught in the Fermi bubble's expansion. As these clouds were shredded by the original eruption, their debris might have collapsed into ultra-dense knots, where turbulent magnetic fields now accelerate particles to near light speed, generating focused beams of gamma rays. Picture a hurricane tearing through a forest, leaving behind scattered trees except here, the trees are spinning dynamos of plasma, turning destruction into cosmic lighthouses. But the radio signals add another layer of intrigue. In 2018, the Mercury Array in South Africa mapped the bubble's edges with unprecedented clarity, revealing bizarre cap structures where radio waves twist into spiral patterns. This polarization suggests the presence of enormous magnetic fields far stronger than those surrounding our galaxy's central black hole. How could such orderly magnetism persist millions of years after the initial eruption? The answer might lie in the gas clouds themselves. As the original explosion plowed through the Milky Way's halo, it could have swept up and compressed primordial gas, igniting a self-sustaining dynamo effect. Like a snowball rolling downhill, gathering mass and momentum, these compressed clouds may have generated magnetic fields that grew stronger over time, etching their signatures into the radio waves we detect today. The most tantalizing clues come from the bubble's gamma ray hotspots, regions where the emission spikes inexplicably. One such zone, near the northern bubble's base, flickers with a 12-day cadence, as if timed by some cosmic metronome. No known object, not a pulsar, not a black hole, occupies this space. Yet the rhythm persists, leading some researchers to propose an audacious idea. What if the Fermi bubbles aren't relics at all, but active structures still being fed by our galaxy's core? In this scenario, intermittent jets from Sagittarius A, our central black hole, could be injecting fresh energy into the bubbles, lighting up these hotspots like bulbs on a frayed wire. Supporting this, the Chandra X-ray Observatory recently detected faint wisps of superheated gas snaking from the galactic center toward the bubbles, a potential power cable, still humming with current. Yet skeptics argue the signals could be illusions of perspective. Gas clouds between us and the bubbles might lens or scatter background radiation, creating phantom patterns. Others suggest the emissions stem from annihilating dark matter particles, a controversial claim given the bubble's sheer scale. What's undeniable is that these structures are rewriting galactic archaeology. They're not just fossils of a violent past, they're dynamic theaters where gas, magnetism, and gravity conspire to produce phenomena we've yet to fully name. Every anomalous flicker, every twisted radio thread whispers the same truth. Even our own galaxy, seemingly familiar, still guards chapters of its story we've only begun to read. In the silent depths of interstellar space, where gas clouds drift like cosmic fog banks, astronomers have caught something utterly bizarre: spectral lines that dance. These aren't the orderly, predictable shifts we expect from objects moving through space. Instead, they flicker, twist, and jump across the spectrum, as if reality itself were glitching. Take the case of SHGb02+14a, a seemingly ordinary hydrogen cloud near the galactic center. When researchers first trained their spectrographs on it, the emission lines didn't just redshift or blueshift. They split into multiple frequencies simultaneously, wobbled unpredictably, and sometimes vanished entirely. It was as though the cloud couldn't decide how fast it was moving or even what it was made of. The Doppler effect, a cornerstone of astronomical measurement, tells us that spectral lines should shift cleanly based on an object's motion toward or away from us. But these dancing lines defy that principle. One leading explanation points to extreme magnetic fields within the clouds. Imagine a cosmic whirlpool where magnetic forces churn the gas into tiny, spinning eddies, each moving at different velocities. Hydrogen atoms caught in these vortices would emit light at slightly different frequencies, smearing the spectral lines into a blur. Under certain conditions, quantum effects might amplify this chaos, causing electrons to jump between energy states unpredictably, like a flickering neon sign powered by a faulty transformer. But magnetism alone doesn't explain the most perplexing cases. In 2022, the ALMA telescope spotted a gas cloud in Orion where carbon monoxide lines appeared to anticipate velocity changes shifting before the cloud's observed motion could account for it. This eerie behavior has sparked radical theories, including the possibility of entangled quantum states spanning vast distances within the cloud. If true, particles on one side of the cloud could know about changes happening light years away instantaneously, bypassing Einstein's speed of light limit. Skeptics counter that turbulence or hidden shock waves could mimic these effects, but simulations struggle to reproduce the precision of the observed anomalies. The implications ripple far beyond academic curiosity. If quantum phenomena or undiscovered magnetic interactions shape these signals, we might be glimpsing a hidden layer of physics that operates only in the vacuum of deep space, a realm where the rules we've tested in Earth's labs no longer apply. Every flickering line, every impossible shift is a cipher waiting to be decoded, hinting that the universe's quietest corners might be its most revolutionary classrooms. What makes these dancing spectral lines so mesmerizing isn't just their defiance of expectations, it's the way they force us to reconsider the very tools we use to measure the cosmos. Like trying to track a hummingbird's path with a sundial, our instruments might be catching only fragments of a far richer, far stranger story. Whether the answer lies in quantum entanglement, magnetic mayhem, or something entirely new, one thing is certain: the universe loves to keep us guessing, and these spectral pirouettes are its latest, most enigmatic performance. The Coalsack Nebula has always stood out in astronomical surveys not for what it emits, but for what it absorbs. This dense, light-swallowing cloud, often called the Great Dark Spot of the southern Milky Way, blocks the glow of background stars so thoroughly it appears as a hole punched through the cosmos. But in 2020, radio telescopes picked up something unexpected threading through that darkness, a chorus of faint, structured whispers at frequencies between 800 and 400 MHz. These weren't the random hiss of cosmic noise, they pulsed with a peculiar cadence, fading in and out like a distant radio station struggling to cut through static. What makes these whispers so puzzling is their origin point. The coal sack, unlike star-forming nebulae, lacks the energetic young stars or shockwaves typically associated with radio emissions. Its cold molecular hydrogen and dust should be virtually silent at these frequencies, yet the signals persist, clustering in pockets where the nebula's gas is densest. One leading hypothesis suggests we might be detecting the fingerprints of exotic particle interactions, processes that occur only in the extreme cold and near absolute vacuum of dark nebulae. At temperatures just 10 degrees above absolute zero, hydrogen molecules can form fragile, loosely bound pairs called dimers. When cosmic rays tear through these dimers, they might release energy in precise radio frequencies, like a tuning fork struck in the void. But another theory ventures into far stranger territory. The coal sack's whispers show slight but consistent frequency shifts, patterns some researchers argue resemble the search signals proposed for interstellar communication. Unlike the chaotic bursts of natural cosmic static, these emissions occupy narrow bandwidths, similar to human-made radio beacons. Skeptics counter that the nebula's turbulent magnetic fields could focus ambient radiation into artificial seeming beams, creating illusions of structure. Supporting this, recent observations revealed the whispers intensify when the nebula passes in front of bright background galaxies, as if its dust were acting like a cosmic amplifier for distant energy sources. The most tantalizing clue emerged last year when the Atacama Large Millimeter Array caught something unprecedented: simultaneous radio and submillimeter emissions from the same coal sack regions. This pairing defies conventional astrophysics, since the mechanisms generating each type of radiation normally operate under wildly different conditions. One provocative explanation involves spin-polarized hydrogen, a theoretical state where the spins of a cloud's atoms align under extreme magnetic fields, enabling energy release across multiple wavelengths. If confirmed, it would mark the first detection of quantum-scale physics playing out on a nebula-sized stage. Whether the coal sack's whispers stem from undiscovered particle behavior, magnetic oddities, or something even more profound, they underscore a humbling truth. The darkest corners of space aren't silent, they hum with subtle, secret frequencies, waiting for instruments sensitive enough to hear them. Every flicker from this cosmic shadow hints that even the emptiest voids might crackle with phenomena we've yet to name. The Boötes void isn't just empty, it's aggressively empty. Stretching 330 million light-years across, this cosmic desert contains so few galaxies that astronomers initially thought their instruments had failed. Yet in 2018, something impossible echoed from its depths, radio waves bouncing back to Earth after a delay of decades. These weren't reflections off nearby objects, they matched transmissions from the 1970s, as if the void itself had been silently holding our signals hostage before finally releasing them. The first confirmed echo arrived via the Arecibo Observatory, a faint but unmistakable replica of the WOW signal, broadcast 41 years earlier. But the real shock came when researchers triangulated its origin. The signal hadn't rebounded from a star, a planet, or even a rogue black hole. It seemed to originate from the Boötes void's central nothingness. This sparked a radical theory. Could the sparse gas clouds drifting through the void mere atoms per cubic meter somehow act as cosmic mirrors? Under normal conditions, interstellar gas scatters radio waves like fog scatters light. But the Boötes void isn't normal. Its extreme emptiness means even sparse hydrogen clouds stretch over incomprehensible distances. If these clouds contained microscopic dust grains or ionized plasma arranged in just the right configuration, they might form a whisper wall, a diffuse reflective surface capable of bouncing back coherent signals over millennia. Think of sunlight glinting off a swirling disco ball, except the ball is light years wide and the glints take lifetimes to return. Critics argue the energy loss over such distances should render echoes undetectable. Yet 2022 simulations revealed a tantalizing loophole. If the original signal passed through a region of collapsing gas, the resulting shockwaves could compress the cloud's atoms into temporary sheets, creating fleeting reflection points. It's like shouting into a canyon as its walls slowly collapse. The echoes might return distorted, but they return. The most perplexing echo surfaced in 2023, a near-perfect replication of a 1975 Soviet radar pulse aimed at Venus. This time the delay matched the Boötes void's exact distance, suggesting the void isn't just reflecting signals but archiving them. If true, we might be hearing our own cosmic footsteps, reverberating through a void that refuses to let silence have the last word. Whether these echoes stem from quantum-scale oddities in ultra-diffuse gas or something even stranger, one thing is certain: the emptiest place we know might be hiding the universe's most patient conversation, a dialogue where every word takes decades to reply. Deep within the Taurus molecular cloud, one of the coldest, darkest regions of our galaxy, astronomers have stumbled upon a phenomenon that defies explanation: a chorus of harmonic radio waves so precise they resemble a cosmic symphony. These aren't the chaotic screeches of turbulent gas or the monotonous hum of background radiation. They're layered, rhythmic frequencies, some cascading in perfect mathematical intervals, as if the cloud itself were resonating like a colossal, interstellar tuning fork. What makes these singing clouds so baffling is their structure. Natural molecular clouds typically emit radio waves in broad, noisy bursts, the result of random collisions between particles. But these signals are different. They cluster around specific harmonics with frequencies mirroring the ratios found in musical chords. One particularly striking example, detected in 2021 near the cloud's core, produced a near-perfect B-flat major triad, a combination of frequencies so mathematically precise that researchers initially suspected instrument error. Follow-up observations confirmed the pattern, deepening the mystery. Theories struggle to account for this eerie harmony. One camp suggests ultra-dense gas clumps, compressed by shock waves from nearby supernova, might vibrate like enormous bells when bathed in cosmic rays. Another proposes that crystalline ice particles common in these frigid clouds could act like microscopic tuning forks, resonating at specific frequencies as they're jostled by magnetic fields. But the most tantalizing idea involves quantum vortices, swirling currents within superfluid hydrogen that, under extreme cold, might synchronize their motions to produce coordinated emissions. Yet skeptics point out a glaring inconsistency. These harmonic signals don't behave like any known natural oscillator. They shift keys unpredictably, sometimes sustaining a single note for hours before sliding into a completely different frequency set, behavior more reminiscent of a radio dial being twisted than any astrophysical process. Even stranger, certain harmonics appear only when the clouds are backlit by distant quasars, as if the light itself is triggering a hidden resonance. The implications ripple beyond curiosity. If molecular clouds can sing, their harmonies might offer a new way to probe these opaque regions. Just as geologists use seismic waves to map Earth's interior, astronomers could decode these radio harmonies to unveil the hidden structures within gas clouds, their densities, magnetic fields, even the presence of unseen dark matter. What lingers, though, is the unsettling beauty of it all. These clouds, once considered silent and static, now hum with a complexity that borders on artistry. Whether the universe is playing an accidental melody or composing with intent, one truth emerges: the cosmos speaks in more voices than we ever imagined. and we're only beginning to learn its language. Cygnus X3 isn't just another cosmic oddity, it's a celestial shapeshifter, notorious for flickering between identities like a cosmic undercover agent. Classified as a microquasar, this binary system pairs a dense neutron star or black hole with a companion star, gobbling up stellar material and spewing out twin jets at near light speed. But what sets Cygnus X3 apart isn't its appetite, it's the bizarre way its high-energy emissions reach Earth, scattered, distorted, and sometimes arriving in eerie multiples, as if the universe itself were playing a game of interstellar telephone. The anomalies first caught attention in the 1990s, when gamma-ray telescopes detected sudden flares from Cygnus X3 that seemed to defy the laws of energy conservation. One day it would blast X-rays with the force of a supernova, the next it would vanish from certain wavelengths entirely. Even stranger, some signals appeared to arrive twice, identical bursts separated by hours or days, like cosmic déjà vu. The leading culprit: vast invisible gas clouds drifting between Cygnus X3 and Earth. These interstellar fog banks, rich in ionized hydrogen, don't just absorb radiation, they can bend and delay it, creating the illusion of multiple outbursts from a single event. Picture a spotlight shining through a swirling mist, the beam fractures casting shadows that move out of sync. That's Cygnus X3's light, twisted by the very fabric of space it traverses. But the plot thickens. In 2014, astronomers noticed something inexplicable. Cygnus X3's radio emissions sometimes preceded their corresponding X-ray flares by up to 12 hours. This reverse causality, an echo arriving before the shout, should be impossible under standard physics. One radical theory suggests the gas clouds might be warping spacetime itself, creating microscopic wormholes that let information slip backward in time. A less dramatic but equally mind-bending explanation involves slow light effects, where turbulent plasma in the clouds slows high-energy photons to a crawl, while lower-frequency radio waves slip through unimpeded. The most tantalizing clue emerged in 2021, when the Chandra X-ray Observatory caught Cygnus X3 in the act of beam switching. Its jets, typically fixed in orientation, abruptly twisted 90 degrees, a maneuver akin to a lighthouse pivoting its beam mid-rotation. This sudden shift coincided with a flare that arrived 3 times at Earth, each iteration weaker and redder than the last. The likely cause: a dense gas cloud passing directly through the jet's path, refracting its light like a prism while also nudging the jet's magnetic field off-axis. What makes Cygnus X3's antics so transformative isn't just the chaos they reveal, it's the way they force us to rewrite the rules of cosmic observation. Every distorted signal, every time-bending echo underscores a humbling truth: between us and the universe's most violent objects, there's often an unseen puppeteer, the ghostly gas clouds that stretch, delay, and sometimes even rewrite the messages they carry. Whether they are cosmic lenses, time warps, or something stranger still, one thing is clear: in the theater of the cosmos, the stagehands might be just as fascinating as the stars. The cosmic microwave background, the faint afterglow of the Big Bang, paints the universe in subtle temperature variations, a quilt of warm and cool patches telling the story of our cosmos's infancy. But one patch defies explanation: the so-called cold spot, a region in the constellation Eridanus chillingly colder than surrounding space by about 70 microkelvin. At first, astronomers dismissed it as a statistical fluke, a cosmic accident in an otherwise orderly backdrop. That is, until radio telescopes caught something impossible: faint, structured emissions within the cold spot itself, pulsing at frequencies that shouldn't exist in such an ancient, quiet corner of the sky. These signals don't match the smooth, diffuse radiation expected from primordial gas. Instead, they cluster in narrow bands, flickering like a dying ember refusing to fade. One leading theory suggests the cold spot isn't just empty space, it's a vast bubble carved out by an ancient collision between our universe and another, a relic of multiversal contact. If true, the secondary emissions might come from gas clouds stretched thin along the bubble's edges, their atoms excited by lingering energy from that cataclysmic encounter. Picture a soap bubble popping in slow motion, the remnants of its film still shimmering with residual motion, but there's a twist. Detailed spectral analysis reveals some of these emissions bear the chemical fingerprint of modern elements: carbon, oxygen, even traces of nitrogen, elements that shouldn't reside in a region this old unless something has been stirring the cosmic pot long after the Big Bang's initial brew. This has led to an even wilder proposal: the cold spot might be a shadow cast by an intervening supercluster of galaxies, its gas clouds so dense they've absorbed background radiation unevenly, leaving behind a cold imprint. Yet even this explanation struggles to account for the dynamic nature of the signals, which vary over timescales as short as weeks. Gas clouds, even massive ones, shouldn't change that fast. The most tantalizing clue lies in the signal's polarization, a slight twist in their electromagnetic waves that hints at the presence of powerful magnetic fields. If confirmed, this would imply the cold spot isn't a passive relic, but an active structure, its gas clouds threaded with invisible forces still shaping the space around them. Whether it's a window into another universe, a cosmic mirage, or something entirely unforeseen, one thing is clear: the cold spot and its whispers are forcing us to rethink not just the origins of our universe, but what might still be lurking in its quietest corners. At the heart of our galaxy, where stars swarm like fireflies around an invisible giant, Sagittarius doesn't just lurk silently, it erupts. This supermassive black hole, 4 million times heavier than our Sun, regularly unleashes bursts of X-rays and radio waves so intense they can outshine the entire galactic center for hours. But what's truly baffling isn't the violence of these outbursts, it's the way they change as they travel through the tangled web of gas clouds surrounding the black hole, emerging distorted, delayed, or even split into multiple echoes like a cosmic hall of mirrors. Take the flare of 2019, catalogued as SHGr event #12, when telescopes first caught the eruption, it appeared as a textbook X-ray, spiky, sharp, symmetrical, and brief. But 7 hours later, radio observatories detected an identical burst, this time smeared across lower frequencies and trailing ghostly after pulses. The culprit, a dense molecular cloud nicknamed the Bouncer, drifting between us and Sagittarius A. As the black hole's radiation plowed through this fog of ionized gas, electrons scattered the light like pinballs, slowing some wavelengths more than others and stretching milliseconds into minutes. It's as if the universe hit a cosmic, slow-motion button, revealing details in the flare that would have otherwise blurred past undetected. Yet stranger still are the shadow flares, bursts that arrive before their visible counterparts. In 2022, the New Star Telescope recorded gamma rays from Sagittarius A that flickered in perfect sync with radio echoes detected 3 days earlier. This impossible reversal hints at gas clouds acting not just as filters, but as time machines. Here's how: when light skirts the edge of a black hole's gravitational well, it can take multiple paths to reach it, some longer, some shorter. If part of a flare's energy loops around the black hole while the rest barrels straight through intervening gas, the delayed, straight-shot radiation might arrive after its detoured sibling, flipping cause and effect on its head. But the real enigma lies in the bursts that shouldn't exist at all. In 2023, the James Webb Space Telescope caught infrared flashes from Sagittarius A that matched no known emission pattern. These pulses didn't align with the black hole's feeding cycles or the predictable orbits of nearby stars. Instead, they traced a perfect Fibonacci spiral in their timing, a mathematical sequence found in sunflowers and seashells, but never before in black hole activity. The leading theory, a chain reaction within the surrounding gas clouds, where magnetic fields twisted by the black hole's spin snap like overstretched rubber bands, releasing energy in rhythmic cascades. What makes these galactic center bursts so transformative isn't just their spectacle, it's the way they force us to reconsider gas clouds as active players in cosmic storytelling. These aren't passive screens filtering light, they're dynamic instruments bending, amplifying, and sometimes even composing new signals from the chaos. Every distorted flare, every impossible echo whispers the same truth. To understand the monster at our galaxy's heart, we must first decode the whispers of the clouds that shroud it. From the eerie precision of the WOW signal to the ghostly whispers of the Coalsack Nebula, these 25 cosmic enigmas paint a portrait of a universe far stranger than we ever imagined. Each signal, whether repeating, vanishing, or defying classification, chips away at our assumptions, revealing gaps in our understanding that interstellar gas clouds only deepen. These vast drifting labyrinths of molecules and magnetic fields don't just obscure our view, they distort, amplify, and sometimes even fabricate signals that leave us questioning reality. Take the Fermi bubble's gamma-ray filaments, or the dancing spectral lines of aquila, phenomena that blur the line between natural processes and something almost orchestrated. Gas clouds act as cosmic prisms, bending light into unrecognizable shapes, while their turbulent interiors generate emissions that mimic intelligence. Even the most promising candidates for extraterrestrial contact, like the HD 164595 transmission, crumble under scrutiny when these nebulous intermediaries enter the picture. It's as if the universe invented its own camouflage, weaving illusions from the very fabric of space itself, yet these mysteries aren't dead ends, they're invitations. Every unsolved signal pushes our technology further, demanding sharper telescopes, smarter algorithms, and more creative thinking. The Cold Spot's whispers, Cygnus X3's time-bending echoes, and the Taurus Cloud's harmonic radio chorus aren't just puzzles, they're breadcrumbs leading to new physics, hidden dimensions of reality we've yet to name. So where does this leave us? At the frontier of discovery, armed with curiosity and tools evolving faster than ever before, the next generation of observatories, like the Square Kilometre Array or the Vera Rubin Observatory, might finally untangle these knots, or they might reveal deeper layers of the cosmic riddle. One thing's certain, the answers won't come easily, but that's the thrill of it. The universe isn't just handing us its secrets, it's daring us to listen more closely, to question more boldly, and to embrace the beautiful uncertainty of the unknown. As you look up at the night sky tonight, remember, every patch of darkness might hum with signals we can't yet hear. Every wisp of interstellar gas could be sculpting messages we're only beginning to decode. The greatest chapter in this story isn't written yet, and who knows, the next breakthrough might come from a data sleuth, a sudden flash of insight, or maybe even you. Stay curious, the cosmos is still talking. Are we ready to listen?